The Ohio State University. She will talk about experimental design for prediction of physical systems, using calibrated computer simulators. So we are very much looking forward to your talk.
Thank you. And I would like to thank the organizers very much indeed for inviting me to give this talk. It's going to be very different from the other talks so far that we've seen in this conference. In particular, I don't really know what the true model is, so I'm going to be using very simple Gaussian process models with constant means. So that's one area that maybe can be improved in the future. As I put this talk together, I found all kinds of different things that need doing. So please, I hope this will just give some ideas for people that you might want to look into some of the things I mentioned. So my background is in experimental design, and I work mostly with industrial engineers, so the kinds of problems that I come across are somewhat different from the ones we've been hearing about. So I'm going to, I can work this out. There we go. So the outline of the talk is, I'll first of all tell you about an injection molding experiment, which was the motivation for a lot of this work. And the experiment has multiple outputs which we want to minimize simultaneously, which of course is not always possible. And we have a simulator that is biased, and I will tell you about all of those things as we go along. Then what we're going to do is use a Bayesian calibrated predictor. This is not new. I'm just using the standard Kennedy and O'Hagan calibration model, for those of you who know what that is. And what I'm talking about calibration is I want to calibrate the bias simulator so that I can predict the means of the physical system. I'm not trying to calibrate the parameters in the model. I don't know what the model is, and even if I could calibrate the parameters precisely, that's not what is of interest to the engineers. What's of interest is finding the means of the physical system, being able to predict those. Then I'll take a little detour here and talk very briefly about experimental design for prediction of a single physical mean with a calibrated predictor over the entire input space. And these will be like one-off designs. You pick the design and then you do the whole experiment, which actually some of the industry people I've worked with, that's all you can do, because the management doesn't give you enough money to do a whole series of experiments. You have to plan it all up front. For this particular problem, we could do a series of experiments. So we did some sequential design. So I'll talk about the sequential design methodology and its assessment developed for this injection molding experiment. We'll assess it on a fictitious example and then look at the results of the experiment afterwards. So I hope I don't run out of time too badly. Okay, so the injection molding experiment was done jointly with first of all, all of this work is done with my colleague Thomas Santner and our joint students Po-Hsu Allen Chen and Erin Leatherman, who did another portion of the work. Our collaborators for the injection molding experiment came from the Department of Integrated Systems Engineering at OSU. Okay, so injection molding, this is a diagram of what happens. You put plastic pellets into this hopper here. The screw here turns and it moves the pellets forward, and the friction of moving the pellets together with the heaters on the outside here melts the plastic. It accumulates at the front here. When there's enough accumulated, this screw acts like a plunger, and it pushes the molten plastic into the mold here. So that's the flow stage. Then you want to get rid of air bubbles and such like, And so they then increase the pressure and they pack more material into the mold. That's the packing stage. Then the mold is allowed to cool. That's the cooling stage. And then the part is ejected. So their goal is to determine which, I'll call them process control variable settings, so the things that they can adjust on this machine so that they minimize the shrinkage of the molded plastic components. So they're interested, for example, in a camera body where you have a little window and a lens has to be put into the window, so you can't have too much shrinkage of the plastic when you take it out of the mold, because otherwise the lens isn't going to fit. So they want to minimize the shrinkage of the various different objects they're making. So we're going to actually measure relative shrinkage, which is the mold dimension minus the part dimension over the mold dimension, usual thing. Okay, so we did the experiment on this plastic part. This is a standard plastic testing part, and they could manipulate 4 variables. These are our control process variables: the melting time for the plastic, the packing time for the extra push of the material into the mold, the extra packing pressure, and the cooling time. So those are the 4 variables. Most of the time I'll just talk about x1, x2, and x3, or even a vector, just x. So those are what we want to find the settings for. They measured 10 relative shrinkages on this part here. They measured the lengths, widths, and thicknesses of these 3 parts labeled P1, P2, P3, and also the total weight. Today I'm just going to talk about the shrinkages and the 3 lengths, so that we can visualize some 3-dimensional pictures. Okay, so the goal again then is to find the process control variable settings, that's the x's, that minimize the mean relative linear shrinkages, L1, L2, L3, of the lengths of those 3 parts. Okay, so we could take some physical observations from this machine. They have a machine at OSU. The number of observations we could take was limited because, firstly, there was a limited amount of raw material. The molding machine time, it's used as a teaching tool, so there's only a limited amount of time we could have on that. And similarly, the technology specialist who ran the experiments, his time was limited. And this would be the same in a factory. If you were trying to run an experiment during the normal production, you can only have a certain amount of time. When we tried to run an experiment at Jaguar Cars once on engines, they gave us, I think we could have 4 days, and we wanted to do a 2-stage experiment, so we chose Thursday, Friday, gave us the weekend to update our design, and then Monday, Tuesday. And as far as the management was concerned, that was 1 experiment over 4 days. As far as we were concerned, it was a 2-stage experiment. Okay, so physical observations are limited, but there's a simulator. This is a commercial simulator, but you can define the part geometry, so that looks very much like the ones we were producing. And this simulator takes okay, so we don't know exactly what equations are in it. It's some generalized Newtonian fluid assumptions are in the simulator, but as far as we're concerned, it's a black box. And it has 7 inputs, so those same 4 process control variables plus 3 heat transfer coefficients. And the heat transfer coefficients, they're there, they're fixed, they're unknown in the physical experiment. Okay, so these we could, if we could do a lot of physical experiments, we could probably try to narrow down the true values of these, but we can't do lots of physical experiments, so we're saying they're fixed but unknown in the physical experiment, but we do know the reasonable ranges, so we can at least operate within a certain range. This simulator, unfortunately, turned out to be biased. Okay, so here are the physical observations. Here's the shrinkage and length of part 1, part 2, part 3. we took 19 different settings of the process control variables, which I'll explain where they came from later. And these are our 19 physical observations. We then took 35 runs of the simulator, again varying the both the control variables and the heat transfer coefficients. And there are simulator observations, so clearly we have to deal with this bias, or this, what I'm going to call discrepancy here. So this is not unusual to have bias in simulators, because I think somebody said this the other day, most computer simulators are based on simplification of physical principles. And calibration, in the way that I'm going to use it, is a process of aligning the output so that the computer simulator output will be close to the mean response you would get from the physical system. So that's the goal. Okay, let me just mention some notation. So the x's we've seen before, those are the control variable inputs. There are dx of those, dimension of x, dx of those. Then we've got these calibration parameters, which in this context are the heat transfer coefficients. So we've got a vector of dimension t of those, dt. We've got observations on the physical system, yp. We've got observations on the simulator, ys. Okay, so let me talk briefly about the model we're using and the calibrated predictor. These are standard models and predictors. So the physical system, as usual, is our observations, our realizations of a random variable, random vector, with a given mean, which we don't know, that's what we want to know, plus some kind of errors, and we take our errors to be identically independent, identically distributed normal errors. The simulator we're going to model as the outputs we're going to model as a realization of a second order stationary Gaussian process. I'm going to take a fixed mean. I'm not going to try and model the mean because I don't have enough information to be able to say what that looks like. That's the precision of the Gaussian process. And then we have some correlation parameters. So the Gaussian process covariance is going to look like this. This is a product Gaussian correlation structure here. These correlation parameters are the correlations between the outputs when you change one of the dimensions in the input vectors by half of its range. Okay, so we have a model now for the simulator output. We have a model for the physical output, and we want a model for this discrepancy. So again, the bias is defined to be the difference between the mean of the physical system at a particular control vector input and the simulator output you would get at that same control variable vector, and if you knew what the true values of the calibration parameters were. So this is the formula for discrepancy, and I want to model that. So so we're taking this discrepancy or bias as a realization of a second Gaussian process, mean zero, given precision, and again a product correlation structure with given correlation parameters, and all of our Gaussian processes and the error process are taken to be independent for now. Okay, so then we can go back and get a model for the mean of the physical system, because the mean of the physical system is the simulator plus the bias. So our model for the mean of the physical system is now the process for the simulator plus the process for the bias. And we're going to model this in a Bayesian way, and I'm not going to give you the details of the priors. Okay, so we need a predictor of the output at all the places we haven't observed. So it's going to be then the sum of the predicted simulator output and the predicted discrepancy. So in other words, it looks like this: the expected value of the simulator process and the bias process, given the data that we've got so far. And then you can compute that by conditioning on the all of the parameters in the model, and then taking the expected value over the parameters. Okay, so this is the set of all the parameters that have cropped up so far in the talk. The phi here is the unknown best value of the calibration parameter, and what I mean by best is, I mean the value that's going to give us the best predictions of the physical means.
Angela,
Yes.
In the language of this week, I think
Yes.
the phi, I think, might be the solution. That's the inverse problem part, right?
This would be the inverse problem if you were trying to estimate that, right? Yes, yes. So, so that many of the talks so far have been on estimating these unknown parameters, and I do want to estimate them, but I don't particularly need them to be the exact value of the heat transfer coefficient. I need them to be some value that's going to correct the bias in the prediction. So that's a little bit different from what we've been talking about so far in the conference, I think. Okay, so just to remind you, before calibration, that's what we had. So now what we want to do is we want to compute this base. Okay, sorry, another question here.
Just a real quick question on how you're using like the definition of bias here. So if you don't know the true coefficients values, how can you say that the simulator is biased and not just that if you had them, you'd actually get the right answer out and that the simulator is correct?
Oh, if I had them, well, okay,
Yeah, so
that's a good question. If I had precisely the exact true value of the simulator, okay, you would, I think what you're saying is you would hope it would be down here. But what we've done here is we've run 35 observations at different values, that may not be the right ones, of the simulator, and they're all up here.
Okay.
So that's what I'm trying to correct. I may never be lucky enough to actually observe this at the correct value of the calibration parameter. Okay, so we're going to, so we're taking these two sets of data, we're building the model, we're getting the calibrated predictor, and we're going to predict, we're going to take the x's that produce these physical observations and predict what the mean of, remember these have got error in them, these are physical observations, we're going to predict what the mean observation would be at those same x's. So I'm going to blow up this corner of the picture, and we hope that our calibrated predictions are going to be very close to what we have here. Okay, so the red is the blown up picture of the physical observations, and the green are our predictions. So our physical observations have error in them, our calibrated predictions will have some kind of error on them, but as far as in the field I'm working in, these predictions are good as a first stage experiment, and then you would go back later and try and refine things. Okay, so let me talk about experimental design options. I haven't said where these observations came from. Okay, so if we're going to do calibration in the form that I'm describing it, we need some physical data and some simulator data. So I need some experimental designs which specify the input values of the control variables and the heat transfer coefficient, the calibration parameters at which to collect the data. Budget is limited again, so I've only got a few physical observations. The simulator is fairly slow running, so our simulator data was also fairly limited. I don't know exactly how long it took to run this simulator, but I know other simulators I've come across, sometimes they can take more than a day to get a single observation. The simulator is deterministic, so if I put in the same x's and t's, I'll get the same answer out up to the computer variability. Okay, design choices. I can decide which set of x's and t's I'm going to observe at the beginning and just do the whole experiment, or I can do this sequentially. And for the problem that I set out at the beginning, it's probably better to do this sequentially, but let me just say a little briefly about single stage designs if you had to design everything up front, hand it over, and have somebody else run the simulator. For physical experiments, it's very common to use factorial designs. Some of you will know what those are, and some of you may not. They are very good if you're fitting a regression model or something like that. They're not so good in the current setting. There's something called an I-optimal design, where you minimize the average prediction variance over the design space for a given model. Okay, we don't really have a given model here, but I'll say a bit more about that in a minute. You could just use a design, space-filling design, as we might do for the simulator experiment. What did we do? Well, unfortunately, what we actually ended up doing was a factorial design, because we were working with engineers and they wanted to have a different way of checking that the predictions matched up what they would normally do with their regression. So we ended up, our physical experiment wouldn't be the best possible experiment for this setting normally. For those of you who know what it is, we did a 2 to the 4th factorial design, which looks at all combinations of high and low, meaning the ends of the ranges, for each of the 4 molding control variables. So they could then fit a linear regression model with first order interactions. And we also added a few what are called center points, which I won't go into, so that you could detect some non-linearity. So that's where this funny number of 19 physical observations came from. It's 16 plus 3. Okay, space-filling designs. These are very common for simulator experiments. I'm not saying they're good, I'm just saying they're very common. And I think Luke from Zato is going to talk more about good space-filling designs, not these, but good space-filling designs on Friday, I think it is. Okay, so what I come across a lot is people using Latin hypercube designs as space-filling designs, and if for certain purposes these are very, very good. For our purpose, they may not be so good. They have input points uniformly spread in each one-dimensional space, but not necessarily in higher dimensions. So if you just pulled a random Latin hypercube design off the shelf and you had 2 control variables, not 4, it might look like this. And for each control variable independently, if you project onto the margins, you would find them nicely equally spaced on that margin and equally spaced on this margin, but it doesn't fill the space very well. So what people often do is they put another criterion on top and say, well, let me pick a Latin hypercube design that satisfies some space-filling criterion. And a common one is maximize the minimum distance between 2 design points, to try and spread all these design points out as much as you possibly can. So that's what that says. Okay, so that was the randomly generated one I just got out of MATLAB. And this one is a maxi-min space-filling design. So the smallest distance between any 2 points in this design is bigger than the smallest distance in this design. And there's a website that actually lists these maxi-min space-filling designs for certain sized experiments. Okay, well that's not all. There are many different papers on different measures of spacing out the design points as much as you can. And I believe the ones that Luke is talking about is none of these, because he's focusing on the criterion of interest. Would that be fair? Yeah? You're looking at something totally different from these, or somewhat different, a little bit different. Yeah. Okay. So these space-filling designs, not the one he's going to talk about, these space-filling designs may not be the best for predicting the mean of a physical process, and and an earlier paper of Luke's was pointing out that you really should tailor the criterion for your choice of design to the goal of interest rather than just trying to space out the design points as much as you can. And our criterion of interest is prediction, and so that would bring us back to a local IMSP optimal design criterion as one possibility. And I don't really want to spend too long on this because I want to get back to the original problem. But so what we're seeking is a physical design, NP for physical, NP selections of control inputs. I want to design for the simulator experiment, NS selections of the control variable calibration parameter pairs. Then I can define the local IMSP optimal combined design to be the choice of that pair of designs which minimizes the mean square prediction error over a particular set of surfaces. So this, for these kinds of designs, you have to actually guess what the parameters are. Remember, the parameters are things like the precisions and the correlation parameters. So if you fix those, you can then draw surfaces from the Gaussian processes with those parameters and take the best linear unbiased predictor, find the average of that as your mean square prediction error, and then find the designs that minimize the mean square prediction error over that set of surfaces with the fixed parameters. Okay, so here's an example of what a design might look like. So if we look at the circles on this picture, I've just got two x's here, two control variables. Here are the calibration parameters. So for this particular selection of parameter values that I took for the model, this is the design that it spits out for the simulator. The physical design is down here, it doesn't have any t's, so it's down here on the floor. And if we project these down to see what the combined design looks like in the control variable space, you can see together, the two designs together are nicely space filling. It's not a maxi-min design. We've got points fairly close together, and in fact there's a point here, you can see that looks darker than the other. There's 2 points, they're almost on top of each other. And there's some thought that if you want to try and estimate the correlation parameters, it's good to have some points close together because that helps with the estimation. Okay, so this is a conference on uncertainty quantification, so I thought, well, what do I mean by uncertainty? If I've got my design, I've got my design. But what's uncertain is what the surface is that I'm trying to predict. So what I need is a design that's going to be good no matter what, well, this is a tall order, no matter what the surface is. That's not doable, but in the sense that it gives good predictions over a wide range of possible surfaces, because remember, I don't know what's in the simulator. Okay, so in the interest of time, I think I'm going to see if I can just jump through this quickly. Okay, so we looked at a lot of different designs with different choices of the parameters, a couple of space-filling designs, and we wanted to calibrate our model, and we wanted to see how well it predicted in 18 different families of surfaces we took. So we took the simulator surface, we had 2 smooth ones like Gaussian process type surfaces, 2 exponential surfaces which kind of shot up in the corner, and 2 with multiple peaks. Somebody talked about the egg carton surface, so one of those, and then one with the peaks on the edges. And then we made the physical surface to be the simulator plus the bias surface, and we should say 3 because there was also the option of no bias. So 2 different types of bias surfaces plus no bias. So that's six simulator surface families with 3 different types of bias surfaces. That gave us 18 families. From each family we took 30 draws of surfaces and then looked to see how well the designs predicted. And by the measure was the mean square prediction error over a grid of points across the space. And we did this for 8 different sizes of designs. Okay, so I'm not going to go through this whole slide, you'll be relieved to know. So the objective then is to find the physical design and the simulator design. So this is the one where we're going to look over the whole space of physical and simulator designs to come up with a design that's IMSP optimal for a certain, remember I'm choosing the parameters here, and then the choice of correlation parameters. There were 4 choices. These are the correlation parameters for the input variables and the calibration parameters. This is the choice of correlation parameters for the bias surface. There's 4 different combinations here. 4 there, 4 there, that's 12. Then there's a fixed design here and a fixed design here. Okay, so I just want to look at the first one is got from the formula I showed you. The second one here says, well, this is a huge amount of computing time to get the optimal designs here. So this one is more expensive to deal with because it has more inputs. It has the calibration parameters plus the control variables. So let's try fixing that design and then just optimizing over the physical design. That cuts the computing time by about a factor of 10. Or we could do it the other way around, and so on. So I want to focus on this one here where you fix the simulator and you optimize the physical, because that one turned out to be quite a good design. Okay, so in general, not surprisingly, no design outperforms any other design, but comparing amongst the designs we looked at, one that looked pretty good was the one where we fixed the simulator design to be a maximin Latin hypercube design. We optimized over the physical design, and we took the design that was good for predicting a surface that was like a sum of 2 GP surfaces, one for the simulator, one for the bias, when all the parameters for the correlation were set to 0.25. So that's a particular design, seemed to predict well over stationary surfaces, maybe not surprising because they're smooth surfaces anyway. It also predicted pretty well compared with the other designs when the non-stationary activity was near the center of the space. It didn't do so well if the non-stationary activity was on the outsides of the space because there were fewer design points out there. But there was a fixed design, a space-filling design, which I won't go into, called an augmented nested Latin hypercube design that seemed to do fairly well for the non-stationary surfaces. Okay, so let's go back to the original, skip that. Let's go back to the original problem. If we want to predict something specific, sequential designs have been used successfully in the past. The prediction of a minimum using some kind of expected improvement. Derek's work on prediction of a contour. Bill Knotz's work on prediction of percentiles. Okay, so here we're interested in predicting the means of several outputs simultaneously. And let me talk about sequential, talk about Pareto minimization. We saw this yesterday actually. So if you have, again, I've gone down to two outputs here so that we can see it more easily. If you have 2 outputs and this is your set of observations, then, and you want to minimize, then none of these up here are worth considering, because if I look at this point here in the middle, it's got a smaller value of the first mean and a smaller value of the second mean, so I can rule all of these out. So that leaves me with just 5 points which are not dominated by any other point, and that is my Pareto front, and the x's are what I want to get at. The x's that correspond to those outputs are my Pareto set. That's what I want. Okay, so we want to find the Pareto set of 4 of the control variable inputs that minimize the shrinkages of the 3 lengths simultaneously. I need initial designs. That's why I talked a little bit about those other designs. We've got to start the process off to do some kind of sequential design because I have to fit the models. So I'm going to start with some design. I could pick one of those that I mentioned earlier in the talk. We fit the Bayesian calibrated model, get the Bayesian calibrated predictors, which I mentioned earlier. And then we want to use an expected improvement strategy to decide what's the next point going to be. And if this is going to be an observation from the simulator, we also need the next calibration parameter setting. So I can pick from the simulator, I can pick from the physical, I can try to do some calculation to decide which option is better. Today I'm just going to talk about the next observations coming from the computer simulator. The physical, I've got 19 observations, that's all I'm going to have. Okay, so we're going to select by using what's called the minimax fitness function. Okay, so just think for the moment about supposing you could actually know these means, which of course we don't because that's what we're trying to predict. But if you knew these, you'd pick the next x which maximized this thing here, this fitness function, where this fitness function is defined like this. And let me just put into words roughly what this is doing. The maximum here is looking for which output produces the maximum improvement over the means that I have on the Pareto front. And then this minimum, looking over all the points in the Pareto front, says if the minimum is positive, then x is not dominated by any point in the current Pareto set, so it's a candidate to look at next. And then I want to look over all possible x's to find the one that gives me the greatest improvement. Okay, well we don't know the means, but we've got models, so we can take the expected value of the expected improvement function, where these things is the model for our means, like we had before, the sum of 2 Gaussian processes. We can get this we can get this piece in a closed form expression, then do the maximization. Okay, so let me just quickly reiterate here. So we're going to take some data, get the Bayesian calibrated predictors. We're going to do this for each output independently. So here's a question: would it be better to build independence amongst all of our models? We're going to predict the physical means at predict what the true means are at all the points we've actually observed, so these xi's, and determine the current Pareto set from amongst those. Then we're going to look for the next control vector to try and improve the Pareto front and the Pareto set. And if this is going to be done from the simulator, if we've chosen the x, we also need the heat transfer coefficient settings. So we're going to get those by minimizing the sum of the posterior mean square prediction errors here. And again, we can get this formula expectation in a closed form. And so once we have our new x, our new t, we can run the simulator, get a new data point, and go back to step 1, refit the models, redo the predictions again, get the new Pareto front and the new Pareto set. Okay, so does this work is the question, of course. So let's take an example where we know what the answer is. So here's a two-dimensional output. There's the formula up here. Here's what the surfaces look like. This for the first output, the minimizing x's are up here. For this one, the minimizing x's are down here, so they can't be minimized in the same set of x's. Okay, so what we did was we tried to create an example that would mimic real life. So we took this as our real mean, and then we added some observation errors to get the physical observations. For the simulator run, this is just one example, we added various biases. There's no value of the calibration parameters here, which would make this simulator unbiased to get 0 here on the bias. For the initial designs, we didn't take the IMSPE optimal designs, actually. We took here just some independent maxi-min Latin hypercube designs, which is not necessarily the best thing to do. We started with 10 physical observations and 15 observations from this bias simulator. And let me go back a minute. Yeah. Okay, so the truth is in blue. So because I can compute this for this example, I know this is the Pareto set corresponding to this Pareto front. The green points here are the x's that went into the simulator. Here's the biased output. The pink points are the so-called physical observations, and they're here. We've got a couple of them close to the true Pareto front, but most of them are far away because the actual x's we picked are far away from the Pareto set. We fit our calibrated predictor. We calculate the x through the expected improvement function. We find the t's, the calibration parameters, by minimizing the mean square prediction error, and that tells us to take the next point of the x's and the next point here. And then let's just check that we're actually getting the correct value, the correct means corresponding to that point. Yeah, it's right here on the Pareto front. Okay, so we go back with our new set of observations. We refit everything. We get the next x, next t, and that tells us to take the next observation here. And sure enough, there it is, right on the Pareto front. And we do this 10 times. Oh, there's the third one. There's all 10. And you can see that, at least for this example, the procedure works beautifully. It gives you the x's nicely spread. That was one thing we were concerned about, was whether we would clump. But no, it's nicely spread along the Pareto. I'm not very good with this pointer. Here it is. Pareto set here, and it giving means on the Pareto front. Okay, so we did that for several different examples. So now we can see how it works in our real experiment. Oh, yeah, before I do that. Okay, so we started here with 15, the green observation, 15 points from the simulator, and we added 10. Should we have started with 10 and added 15? Should we have started with 2 and added 13? So that's another uncertainty question. So we looked at this for this example, and these are the mean square prediction errors for 100 points along in the Pareto set. And what you see here is, I never like to take the minimum because this is only one example, but maybe we should take between about 6 and 11 points for our initial design, and we certainly shouldn't take only 4. That gives us a very bad prediction error, and that's because with only 4 points we're not fitting the initial models very well. And it's not very good. This is the single stage design, no sequential steps in there at all. so that's not so good. It seems to be, maybe not surprisingly, better to be down in the middle here. So it looks like somewhere in the range 40% to 75% of your total number of runs should be in the initial batch, but that's only one example, so I can't give you a definitive answer. Okay, so let's go back to where we started. We had 19 physical observations, and originally we had 35 simulator ones, but now I want to compare that with the sequential procedure. So let's just take 25 of the original 35. They're as space filling as we could get here. These are the predicted means at the x's and t's that gave us these 19 physical and 25 simulator observations. So these are the predictions after adjusting for the bias. We're trying to minimize all three outputs here, and here we just got one minimizing solution down here. Okay, so now we want to take another observation. So we want to pick the x, we want to pick the t's using the procedure that I described. We did that, and the predicted output is now down here, and it seems to have improved over where we were quite considerably. Okay, well that looks good. Let's do it again, and again, and again. 10 more. Well, we didn't improve much over that. That first jump was quite a big improvement, and after that we didn't improve very much. There are 3 points now down here on our predicted Pareto front. I don't know what the truth is. I can't compare this with the truth. So what can I do? Well, I can try to get some sort of measure of quality, and one measure of quality of a Pareto front is given by this hypervolume indicator. So here's that's not the same example, but here's a Pareto front here, the red points. Pick a reference point, and then find the area between the reference point, the axes, and the step function here between the points on the Pareto front. So that's a measure of quality in the sense that if I now improve the Pareto front and it's down here, my hypervolume indicator will be bigger. So that's one way of assessing how well you're doing if you're comparing between methods. Okay, so what happened for our the experiment we just looked at? This is where we were when we started, and remember that big improvement when I took the first point sequentially, so the size of the hypervolume indicator increased by that amount, and then remember there wasn't much improvement after that. Well, you can see that here. So you could use this to say, well, the system has converged to something, and that's all. That's the only way I have, without running many more observations, to be able to assess this, but other people may have better ideas than this. Okay, here's the value of the hypervolume indicator when we finish. Here's the approximate Pareto front, or the estimated Pareto front that we got with our three shrinkages. The way to interpret this, of course, is if you wanted to minimize the shrinkage in the first part, you would take setting number 2. If you wanted to minimize the shrinkage on the second part, you would take setting number 3. So this is what you give to the engineers, and then that allows them to pick sensibly. Or, better still, do another experiment and try and refine the results that one has so far. Okay, so the single stage design, the one where we didn't do any sequential adding of points, we just used them all at the beginning, notice how much smaller the hypervolume indicator is, and that's because the Pareto front is not pushed down towards the minimum. However, if you take your predictor that you got from here and you do a lot of grid predictions and search around, now you do have some hope of doing as well as we did with this sequential design, at least as far as the hypervolume indicator is concerned. So I now have quite a few settings here of the 4 control variables that I can give back to the engineers. It has reduced the ranges quite considerably. This first one, when we started, the range of melting temperature was going from 180 up to about 230, and you can see we've at least narrowed down to a good range being about 200 to 208, and now we can, if they can do another experiment, then that's the range they would look in. Okay, so design issues, type of initial designs, IMSP optimal designs, or independent maximum Latin hypercube designs, maybe not so good. This augmented nested Latin hypercube designs, possibly some of the designs that Luke's going to talk about on Friday. Total number of observations. If you don't have a budget, well, obviously you want to, well, no, maybe not obviously, you want to take as many observations as you can. So some work that Derek and Ophir Harari did and allowed me to tag along. We looked at calculating a sensible number of observations depending on the complexity of the surface that you were interested in and how accurate you wanted your predictions to be. Should you do a single stage or sequential design? Well, if you're trying to minimize like this, probably a sequential design is the better option. If sequential, what fraction of observations should be allocated to the initial design? So far it looks as though it's somewhere in the middle of the range, 40% to 70%, but that could be refined. What's the best method of choosing whether to add an observation from the physical experiment or the simulator? That's going to depend somewhat on how much error variability there is in the observations and how biased the simulator is. Then other issues that I haven't even touched on that other people have in the conference, well, some of it. The modeling issues, all I've done is taken this very simple Gaussian process models. Haven't talked about choice of priors. Measuring uncertainty in the prediction of the Pareto Front and the Pareto set. There's a nice paper by Benoit Gainsbourg and Roustant in the non-calibration setting. All the models we've fitted have been independent for the different outputs. Can you get a way to build in the dependency to make the procedure work better? We couldn't, but maybe there is a way to do it. Underlying our physical experiment, there were all sorts of things that I've completely glossed over about trends in the observations and things changing over time. So the reason I've only got 19 was that we had to take averages to average out all the trends. But maybe one could take a more accurate mean model rather than just this constant and build it into the update rules. We haven't looked at that. Okay, so thank you very much.
Do you have any questions? Okay, Henry.
There is a small but very interesting literature on minimal bias design. What I loved about your paper is the concentration on bias. This work by Val Fedorov and others. So I wonder if you could sort of sell this as some sort of minimal bias design procedure or something like that.
Yes, that's a good idea. I'll ask you more detail about the references afterwards. Thank you.
Thank you. Sorry, that was very interesting. So you were designing quite carefully to find the Pareto boundary.
Yes.
Yeah. So yesterday I talked about designing much less carefully for finding the inverse of the boundary.
Really?
And I was interested in the set. Yeah.
Oh, well,
So I was interested in it's like all of the control values which would give you like arguably, you know, sort of, if you like, objects which would at least function near the Pareto boundary. Yeah. So there's an interesting poster outside which points out that designing forward to learn about the function and designing for learning about the inverse are not necessarily the same.
Yes,
So I wonder if you want to know, you're recommending to the person the kind of things that you could actually build, rather than saying, here's one that is on the boundary, so that's quite a good one. You could look at the class of them, whether you have any feelings for how you would design, it's an inverse workshop for learning about the inverse of the boundary.
Well, I am trying to find the x's, the control variable settings that will give me point on the boundary, but I'm not. I'm not trying to find the whole Pareto front because I don't have enough information.
But also, you're trying to find individual points on the front. So you're trying to find this x is on the front, so therefore it's a good thing. But there could be many other x's which actually reach the. But anyway, I just wonder if you have any thoughts about designing for the inversion.
Well, I'll talk to you afterwards. I can't do that off the top of my head. Yeah. Okay.
When you were presenting your design for the simulator runs and the physical experiments, and then I think you projected down into the control space and everything was sort of separated out.
Yes.
Very naively,
yes,
you might guess that you want to have some runs where simulator runs at the same control settings of your physical experiment to learn a bit about the bias.
Yes.
Is that a bad idea, or?
No, it's not a bad idea. Hang on. Yeah, okay. So, remember I said there was one, I skipped over this, I'm sorry. I said there was one of the space filling designs that did very well, this augmented nested Latin hypercube design. So this is the extreme of what you're saying, where there's complete nesting. So if I take the simulator design here and I project down into the X space, then it matches. I've got 15 simulator observations and 10 physical observations. So 10 of the simulator here actually match up exactly with the physical. That's the other extreme. So I don't know is the answer, but yes, I think it's probably a good idea. The downside, I suppose, is that there's more empty space. So, don't know. Yeah, I think Luke has that.
I think that in this setting where you have the calibration aspect, I think the combined IMSP criterion, I think it's a very good idea. And I wondered if it can also help you to decide which proportion of observation which proportion, if you fix the total cost of the experiment, including physical and simulation, maybe it can give you an idea on how you have to spread this cost between physical experiments and simulation experiments, if simulations are very demanding in terms of computational time, for instance.
Yes. So how much extra value you would get from taking another?
How you spread the total budget between physical and simulation?
Yes.
I don't know.
No, that's a good idea. Yeah.
There was a question.
So you have shown then this quality criterion. So how good these points are. You showed a plot where the quality criterion leveled off.
Yes.
Can't you just use this criterion as a tool? I mean, to computationally place the points.
Sorry.
That
so
one,
many-
yeah, that
That one?
yeah, the this HI
Yes.
indicator.
So use this to,
Well, you move points around and maximize that one. Say numerically, so by some stochastic gradient algorithm.
you mean in using the predicted?
Right.
Yes, yes. Yes. Yeah. Maybe, yeah.
Just coming back. Oh, sorry. Is your question better than mine? Just coming back to your discrepancy, your delta of x. There's always some identifiability issues
Yes.
with capturing that in certain cases using the sort of Kennedy-O'Hagan framework.
Yeah.
Did you have a look at the shape of that surface once you'd updated it with various of your designs?
Um,
Obviously, it would have a huge offset given your opening
Yeah.
plots, but did it have any physical structure?
We
just
did-
one offset, and some
yeah.
of your designs make more sense.
Yeah, we didn't in this particular experiment, but yeah, should have done.
It can give the
Yeah.
modelers more confidence if they see that their model is looking good except for just a constant offset.
Oh,
Rather than a
yes.
highly structured discrepancy term, which then says that they're missing a lot of physics.
Yes. Yes, we didn't do that, but we should have done. Yeah.
Okay, so perfect. Thank you very much.